the right. And I also have to be below all the points on the left. This immediately gives you that the condition, the necessary condition for that to happen is the slope is 0. Okay? Any question about that? Let's go here. Let's go here. If I'm asking you the following question, find x star that minimizes this red function over the interval a to b. If somebody gave you the answer to be this guy, is it correct or not?
No.
Anybody doesn't agree with this? It's not correct. Why? Because it's simply outside of the feasible domain. We are not allowed to look outside. So, if you are on the boundary, I'm not allowed to perturb delta x positive. I'm not allowed to do that. I'm just allowed to introduce perturbations to the left. So my condition is my point has to be less than, the value has to be less than all the points to the left. This gives you the condition that the slope has to be negative indeed. Okay? This is a very, very important concept. What's that? Is that indeed we're looking for a minimizer x star that is in our domain, the interval, right? But also, when you perturb x star plus your delta x plus your epsilon has also to lie in your feasible domain. This is what we call admissible perturbation. Admissible perturbation. Your perturbation has to be admissible. What do you mean? That is, after the perturbation, we have to be back in the domain. Otherwise, you're comparing with something that is not feasible. It's an unfair comparison, right? This concept is very trivial now, right? It's so trivial. But it will become very serious when you go to the infinite dimensions. So we have to get from here. Any questions so far? Any question about this theorem and this concept? This is all what I need to get from this book. The theorem and this concept. Any question? Yes, please.
Is it necessary that the slope should be negative towards the end?
Yes.
Yes, if you remember what we're saying, if this is really a minimum point, then the slope has to be negative or 0. Less than or equal 0. Yes, it can be positive. If it's positive, this means what? If the slope here is positive, it means that this is the shape of the function. So the points to your left, which are feasible points, they are less than your function. Can be positive. And it's the other way around here. Any question? Any question? This theorem and this concept. Okay, gonna continue. This is 1D, gonna do 2D first. We'll not jump infinite dimensional. We'll do 2D. Okay. 2D minimization. Theorem. Given J, that is now maps, it needs two numbers and gives you a number. So it maps AB, some interval, CD, another interval into Y. Again, I'm going to call this I. Okay? And gives you a real number. So this is actually your domain, X and Y. This is A, B. This is C, D. So this is your feasible domain. Okay? A, B, C, D. The theorem. If X star, Y star minimizes J on theta, which how do you write it? j of this guy less than j of any x and y for all x and y in I, right? If this is satisfied, and if the derivatives exist, partial j, partial x, partial j, partial y, at the start, at this point, at the optimum point, exist, then first, if we are in the middle, so x star, y star is in the middle, so it's in AB, cross CD, both open. If you don't understand anything from this language, please stop me. I'm gonna keep using it to the end of the quarter. And I'll try to guess what you know from this language and what you don't. So, of course, sometimes my guess will not be accurate. You have to remind me. Yes, you?
Is there a reason, for J mapping to R space, should it be R squared? Or
No.
or is it
In finite dimensional optimization, you always have a single objective, right? Yeah, you always have a single objective. You get a number at the end and you want the minimum of this number because there is no meaning for the minimum of a vector. Vector has two components, or you are minimizing both components. So it's a multi-objective optimization. It's as if you have F1 and F2. And actually there is no single way to do it for multi-objective. We don't have a theorem like this for multi-objective. Right? It's you have to tell me which objective you care the most, right? You have to do it weighted, or there are other means like the Pareto optimal. We don't have something for multi-objective in general optimization. It's just playing around actually. So anybody can tell me what's the condition here?
Oh, the derivative should be 0.
What derivative? Partial j, partial what? X.
And y.
And partial j, partial y. The gradient has to be 0, partial j, partial x equals 0, partial j, partial y equals 0. That's correct. And I want to actually derive it from this theorem. So we know the answer here, and you know, guys, that we will have double I, triple I, and so because we have boundaries, right? But let's get this. Let's see how we do it. So I'm going to do the following. I'm going to define large F, and its function of a single value, because I'm going to apply this guy. F of epsilon. Okay? What's this? It is the value at your minimum, the best ever, plus some epsilon multiplied some perturbation. So it's this constant that we were talking about. How we get this theorem? That we have the minimizer and perturb it a little bit. If we are in the real line, we perturb it in the real line, left and right. Now we are not in the real line anymore. We are here in the middle. So if I'm perturbing, what are the admissible perturbations? What are those?
Inside that.
Yes, I can go right, I can go left, I can go up, I can go down, and any direction in between. So this is my perturbation space, okay? As long as the radius is small enough, right? To be in the design space. Any question about that? Okay, so epsilon, I will multiply epsilon actually by some vector eta, where this eta has components, eta x and eta y. So epsilon controls the size of the perturbation. Obviously, we're talking about small enough epsilon, very small values for epsilon. And eta controls the direction of the perturbation. And if I'm in the middle, do you have any constraints on the direction of the perturbation?
No.
No. Okay? So this is for any eta x and eta y. So I'm defining my function of epsilon to be this thing. That's fine. Nobody's going to prevent you from defining anything. Okay, by definition of the theorem says if x star y star minimizes j. So by definition, f of 0, just substitute epsilon equals 0, please. Okay, you get j at the minimum, right? Which is by definition less than j at any other thing. Right? This guy is actually f of epsilon. So look at this red statement. What does it say? I'll give you some time to write. I'm exactly doing what I told you before. We usually have the optimum, perturb a little bit, and compare. So I'm defining some large f. It's a function of the perturbation, the size of the perturbation, okay? So it's j at the optimum, but I'm perturbing a little bit. So I'm not getting the optimum anymore. So if the perturbation is 0, f of 0, just substitute here if epsilon is 0, you get j at the optimum, which is by definition less than any other j, which is simply your function, right? So look at this red statement. What does it say? It says that f of 0 less than or equal f of epsilon for all small enough epsilon, right? Maybe between negative epsilon hat and epsilon hat. Any small numbers, okay? Any small numbers, but can be positive, can be negative. So this red statement says f of 0 is less than or equal f of epsilon for all epsilon in some neighborhood. So what does it imply? What does it imply? What is the minimum? What is the minimum? 0 minimizes f, right? 0 minimizes f. So f is a function of single variable, epsilon. Its minimum is at 0. I mean, this is actually by intuition, yeah, right? Yeah, but we have f as a function of a single variable, and if we know the minimum, then we have a condition. What's the condition? What's the condition? What's the condition? Come on, this is function of single variable. And you're telling me that 0 is the minimizer. So what is the condition for that?
Oh, f prime should be 0.
Yes, so the condition is df, right? D nav, this is a function of single variable. df by d epsilon at epsilon equals 0 equals what?
0.
What? 0. Yes. So let's do that. So df by d epsilon. And I'm going to substitute by epsilon equals 0. So let's write f first just to make it. F of epsilon is j of optimum point plus epsilon times eta. So it's x star plus eta, epsilon eta x, and y star plus epsilon eta y, right? Anybody has a problem if this is our f, right? Applying epsilon times eta, adding epsilon times eta to your minimum. Just to make it clear so that when I'm doing the differentiation, I do it clearly. Why? Because j, from the beginning, j is a function of two variables, x and y, two arguments. Here is the first argument, and here is the second argument, right? So let's apply our differentiation, df by d epsilon equals, I'm differentiating this guy with respect to epsilon, I'm going to use the chain rule. Partial j, partial the first argument, which is x, times differentiation of the first argument with respect to epsilon. What's that? What's the derivative of this guy with respect to epsilon?
Etex,
It's
epsilon.
8x, right? Plus partial j, partial the second argument, which is y, times derivative of the second argument with respect to epsilon. What's that? Eta y. Any question here? Just chain rule. And I'm saying that at epsilon equals 0, which means at the start point, this is equal to 0, right? This is my necessary condition from the 1D minimization theorem. Okay? This statement is not complete yet. It has much more. Remember that this is for all eta x and eta y. We are in the middle of the domain, and you told me that we have no constraints whatsoever on eta x and eta y. Right? Because now this black statement is equal to 0 for all eta x and eta y. What's the implication of that? What's the implication? What? That the addition.
It is not valid on the surface of the function.
And forget about anything else. I'm giving you this statement. I'm telling you that this left-hand side is 0 for all any value of eta x and eta y. What do you get?
Both the terms are equal.
And
Zero.
these things are individually
Equal to
zeros, right? Because if you're telling me that it's true for any value eta x and y, well, what about the following? What about, I'm going to take eta y equals 0, so this vanishes. I'm going to take eta x equal 1. So you immediately get what?
JF by JF
Partial
equals
j, partial x at the optimal point is 0. And I'm going to do it the other way around and get partial j, partial y at the optimum point is 0, which this is your theorem for 2D minimization, right? Is that partial j, partial x is 0, partial j, partial y is 0 at the optimal point. Equivalently, the gradient of j is 0, right? At the optimal point. Okay? Any question? Any question? I'm going to jump to the infinite dimensions. We do it in 1, we do it in 2, we can do it in infinite. Any question? Yes, please.
This time eta x and eta y we can move in all directions, right?
Very good.
What happens if it's on the edge?
If you are on the boundary, this is a very good question. If you are on the boundary here, what will happen? What about eta y?
allowed.
Yeah.
Can be anything, right?
Eta x can only be.
And eta x can be only negative. Or your epsilon can be only negative, right? And if your epsilon is only negative, cannot be positive, so you're allowed for the points to your left, allowing points to your left only, the slope has to be negative, right? So this statement will be modified a little bit, since no condition on y is still valid, but this guy will be less than or equal. Okay?